All right. So I
Okay.
guess without further delay, Didem.
Yeah. So thank you for inviting me. Do I have a screen permit or? Yeah,
Oh,
I do.
you should
Okay.
get.
Okay. So can you see my slides now?
Yeah.
Okay. So today, what I'm going to, first of all, my name is Didem Unat. I'm from Koç University. It's located in Istanbul, Turkey. I'm an assistant professor there. And so today, I will be talking a little bit of a different track that probably Hatim didn't expect such a title, because we tend to do, runtime systems, compilers, and libraries for scientific computing. But last couple of years, we started working on deep learning frameworks, but in terms of system aspects, like parallelization aspects. So today, I'm going to present our recent work on deep learning, accelerating deep learning models, but looking at a system approach. So we represent them as a data flow graph, and we partition the data flow graph. So let me talk first the motivation. Does this show the bar at the bottom? Does it prevent you seeing the slides?
We can see the slide, but the bar is there, but that's okay. I believe it's fine.
Okay, maybe it will disappear. Okay. So deep learning models are compute intensive. So that's why GPUs are very good at training. They can provide like order of magnitudes faster training and have higher memory bandwidth and lots of cores. But the problem with GPUs is they have very, very limited memory. For example, if you look at V100, they come with 32 gigabytes of memory, and technology limitation and price doesn't allow you to go much larger memory. But if you look at DNN models, deep learning models, they grow in size over years because they tend to provide high accuracy. And when I say grow in size, I mean also like they get deeper, more layers, but also wider. And most of the time when you have a wider model, they can they provide faster training. A good example is wide ResNet versus ResNet. So this brings the issue of, single memory, GPU memory is not sufficient to train these models because models get bigger, not just data. And these, there are some models, they barely fit into GPU's memory if you use very small batch size. And small batch size means the resource underutilization. And the models, they don't fit into single GPU, you have to do something with it so that the model can fit into single GPU. So if you look at the related work in this area, I don't know how to make this go away because it will cover some of my slides, but anyways. Do you see this one as well? This.
We do this. Yeah, we do see that. I think
I
on
don't
the
know,
last line.
it doesn't move. Huh, it moves now, maybe here. No. This corner. Okay, maybe here. This one I cannot move anywhere. Okay. So, oops, I went too far. Huh. If you look at related work, there are actually plenty of work focusing on, memory constrained DNNs. And there are some single device-based solutions. In the single device-based solutions, they tend to target memory optimizations, like how much the data that a model occupies. So one popular is a gradient checkpoint. Is if in scientific or in HPC, basically this translates into redundant recompute. And some of utilizes this is similar to most your model is in the all the parameters are in the host memory, and then you retrieve them as needed. But these are single device memory, single device solutions. So for distributed training, we have data parallelism, model parallelism, and hybrid versions of them. In the data parallelism, it doesn't really address the memory issue because you don't shrink the model. You just divide the data in multiple input data in multiple devices. In the model parallelism, people, the naive initial approaches, they don't really address the memory issue, but the ones that address, like gpipe from Google, pipe3 for Microsoft, etc., those are model specific. They are not very general, or they introduce this accuracy issue, or they require manual tuning or intervention by the programmer to partition the model among multiple devices. There is also mesh TensorFlow from Google, and this is also very specific to transformers, NLP, natural language processing domain, and requires manual tuning, partitioning as well. So these are the related works, but our approach is generic. We have zero dependency on DNN, or require no knowledge about deep learning aspects of the models. And it's automated, non-intrusive. We don't change the neural network model or its kernels. And we work at the system level, which makes it very smooth. So you can give us any deep learning model and we will be able to partition it. So because we operate on the computational graph. So you guys are probably familiar with computational graphs, but in terms of deep learning, most popular frameworks like TensorFlow or MXNet, they deep learning model into computational graph before they process it. And these graphs are mostly static. There are some dynamic ones, but most of the time, the structure, dependency, its shape doesn't change. But at the same time, we see this graph in HPC as a task graph because there's a dependencies between nodes. What's missing is how much each of these nodes costs, like how much computation you do in each node, and the communication. The edges represent the communication between the nodes, how much data you need to move. So this information doesn't initially come by the TensorFlow or MXNet. We need to profile and get that information, and we do that. So then the question is, how to partition this task graph among multiple GPUs? It becomes this question, like model parallelism, we translate this actually into the new question, which is how to partition this graph among multiple GPUs so that you obey the memory constraint. Each partition will fit into single GPU device. You reduce the communication between partitions, and also you minimize the total execution time at the end of the partitioning. Okay, may I take this one off? Is that fine?
Absolutely, of course.
Okay, okay. I think that was sufficient. Okay. So you may ask that, you know, in HPC, there are a lot of graph partitioners. Why develop your own? So first of all, most of the graph partitioners work on regular graphs, no directed edges. So this is a DAG, directed acyclic graph. So there's this aspect. So DAG partitioners are very few, but the ones that they exist out there, because they are not, their objective is not constrained by memory, that basically the solution they provide doesn't obey the memory constraint of a device. And also most of the graph partitioners, at least the schedulers on them, they work with small number of graph nodes, but in deep learning, we have a very large number of nodes in the graph. Like this can be over 100,000 nodes. These are the actual examples we use in our experiments. I'll talk about them later. So basically, another objective is to have low complexity, low running time of partitioning. So basically, our approach, we take the deep learning model, we create a computational graph with the help of the deep learning framework, which is, and here we use TensorFlow. After we get this graph, we need to annotate it with costs. Like each node need to have its compute time, and edges will need to have communication times. And the scheduler, we need to also know the memory consumption at each node at time t. So, and then this will output, So this will output a annotated graph with cost, and then our partitioning algorithm, we call it PAR-DNN, will partition this into however many devices you have. Let's say you have k devices, it will create k partitions. And here example is there are two partitions, green and pink. And then the output is basically node ID. Each node will have a device ID map to it. So B, for example, go to device 0, C goes to device 1, etc. So this mapping information will be fed back to the deep learning execution engine. For example, TensorFlow backend reads this assignments or the mapping file to be to place the nodes into devices that we recommend, and then it just runs the training based on this assignment. Okay, let's look at the details of the algorithm. The algorithm is divided into two steps. Step 1 and step 2. In the step 1, basically we do the basic partitioning. Given k devices, partition the graph into k partitions so that execution time is minimized. So we look at communication time minimization and the load balancing here. After we have these rough partitions, in step 2, we check whether we meet the memory consumption constraints. If each partition meets the device memory constraints, then we are done. If not, we will handle the memory overflow with another algorithm. So some terminology that I need to explain our partitioning is critical paths. You probably know the heaviest path in the graph. And then there is the term we will use, linear cluster. Linear cluster means a path or a node. And span of a cluster is the time period at which a cluster is executed. Earliest time, the beginning, and the latest time, the last node in the graph executes. So that's we call the span. And that's important for the scheduler. And the memory potential is how much memory a node needs at time t. This is also when we execute a node, it's not only its input data, but output needs to be, we need to have a buffer for the output. Also, in the next, like time t plus 1, you may need to keep its data longer than just the next time step or time t1 because of the difference between reserved nodes or normal nodes, etc. in, for example, in TensorFlow. So that's why we introduced this memory potential to indicate how much memory a node needs at time t. Okay, in the first step of the algorithm, it's further divided into 3 stages. In fact, having these multiple algorithms, heuristics to have the partitioning really lowered our overhead. So partitioning time. So the first is slicing. So first we do graph slicing to obtain coarser view of the graph. And this will also capture the costly communications. For example, in the graph slicing, we first try to obtain k critical paths. So we traverse the graph and create k critical paths. We find the first critical path, we kind of remove that from the graph and find the second critical path, and then the third, etc., until we have k critical paths. Since we have k partitions. And of course, there are other nodes left after we have k critical paths, and we refer to them as secondary clusters. In this figure, for example, pink one is the first critical path. This green is the second critical path. But then if we have k is equal to 2, we have these yellow, purple and blue nodes. Those are a cluster. In the second stage, as you may guess, now we will merge these secondary clusters with the primary clusters in a way that we balance the computation, load, and also minimize the communication. So in the mapping, the first part of the mapping, we merge secondary clusters that have no parallelism gain. If you even you have an additional device and run these in parallel, they won't provide any benefits. And then we looked at nodes to enable load balancing. So we will pick a secondary cluster and merge it with one of the primaries. And this is actually existing load balancing algorithms doesn't really work because we need to do a local balancing rather than global balancing. Why local balancing is more important? Because this graph is executing and the scheduler at some point time t needs to balance the load rather than looking at the entire graph and load balancing. That's why, for example, if you look at the state-of-the-art load balancing algorithm, this node D will be put into green cluster, but in our case, it is put into pink cluster. So this results actually much better load balancing at the execution, actual execution of the graph. Okay, and then after doing slicing and mapping, we have the refinement. I won't go into refinement for the sake of time. Also, it's a little harder to explain in the slides, but this is final makeup on the graph. It enhances the partitioning quality at the cluster level and the node level. What we do is we swap things, swap paths and nodes between primaries to make it final partitioning more balanced. In fact, even though refinement seems, kind of the final tuning, it actually provides 15% improvement in the execution time. So it's by no means it's not important. Okay, now we have, in the first step, now we have K partitions, but we are not sure whether they meet the memory consumption constraints. The second step guarantees that the partitions will fit in, each partition will fit into GPU memory. In order to do that, this again divided into three stages. In the first stage, we emulate the TensorFlow scheduler or the deep learning scheduler. And I'll explain why we need to do that, because in a DAG, we need to know when a node executes. If not, we don't have a good estimation of its memory consumption. again, it's not just what data it uses, it also when its output is needed by the other nodes. So that's why we need to kind of emulate the scheduler to know the order of execution of the nodes. So that's the key part, the order of execution. So here, as an example, let's say we assume a schedule like A, B, C, D, E, F, B, G. This is the order of, sorry, B is not here. A, C, D, F, E, F, B, G. This is the order of execution, scheduling. And the peak memory reserved in this case, for example, B and F will feed into G. So we have 8 units of memory consumption in this schedule. Same graph, but in another schedule. This is part of the graph, by the way, not the entire graph. Of course, you have many nodes before A and after G. So assume another schedule which goes in this order of scheduling or execution within a GPU, A, B, C, D, E, F, G. But this one will require 11 units of memory. As you see, different schedule results in a different amount of peak memory consumption. That's why we need to know or emulate deep learning scheduler. So basically, now we first emulate the scheduler. In the second stage, we model the memory consumption based on the scheduler. So we will derive the memory consumption on a certain device at a certain point in time and calculate the memory potentials that I basically per node at time t, what is the memory consumption? And the last part, now we know the memory consumption in each node, in each device. We need to address the memory overflow. So let's say we have a huge memory consumption in one device, then we need to answer these 2 questions. Which nodes we need to remove from this partition? And when we remove these partitions, where should we put them? Like which device they should execute? So in terms of memory overflow, we treat this as a knapsack problem. So we formulate this 0-1 min knapsack, and we move a set of nodes from one loaded part. So their summation of memory potential at overflow time exceeds the overflow. And the cost of a move is how much it affects the existing partition. And so what we try to do is find a device that incurs the least possible perturbation on the step 1 results. Because in step 1, we really try to minimize execution time and load balance. So when we moved this node to another device, we want the least effect on step 1. And once we handle all the nodes, our partitions will fit into a given number of GPU memory. Of course, there may not be any solution because we may need more GPUs to partition, but if there is a valid solution, we find it. Okay, now I will present some results. By the way, do we have any questions up to here? I didn't ask, or any I feel like maybe I talked too fast, too slow.
No, you find them. Perhaps I have one question. You know, many of us are actually familiar with DAGs, and we were wondering, or at least I am wondering, how wide typically are the DAGs in DNN workflow? How wide are there? I mean, how many degree of parallelism do they expose?
That's a good question. I had a slide about it. I think I may have put into backup slides. So you're right. In the results, you will see that in some cases, we don't have a perfect speed up or sublinear speed up because it's basically because of the nature of the graph. Because as you said, in some models, they're not wide, they're just deep.
Gotcha.
Okay. But some models, they are wide as well. So those are perfect candidates for, partitioning. Also, you will see that, for example, using 4 GPUs give the best improvement. If you go beyond 4, because there's not enough parallelism, it goes down. Your speed up goes down because you don't really need 8 GPUs to train this model. You're fine training with 4. That's
interesting. Yeah, interesting outcome. We also sort of experience on our side during the procurement of some systems that 4 nodes per, a system equipped with 4 nodes are typically a good balance to give performance on the workload.
I think this is also important if you, for example, pay clouds to train your models. You may have this question whether training with 4 GPUs is faster than training with 8 GPUs. For some models, training with 4 GPUs is faster, and you can maybe pay less dollars per hour. So I think it really depends on the nature of the graph. And we have these calculations that I'm not showing here, like communication to computation ratio of the graphs.
I see.
These are, independent of how you partition. It's the nature of the graph tells you communication to computation ratio.
Interesting. Thank you.
Yeah. So these are the models and data sets that we use in our experiments. There are 5 models, but we have 2 flavors of them. Large and very large ones. The very large ones doesn't fit into single GPU memory. Large ones, they barely fit. You may need to use batch size of 1, for example, so that it fits. And we pick these models from different domains like NLP, language modeling, video prediction, computer vision, etc. By the way, it's harder to find large models freely or publicly available large models. I think companies keep them for themselves. They don't disclose these models. So it was kind of difficult to come up with these models. But we try to use the ones people use in their publications. But if you're aware of very large models or you have in your group, we will be happy to test it in our framework. Okay. So the first result that I'm going to show is more like qualitative advantage of our framework. Basically, we allow larger batch size to be used. If you continue with DP is here, data parallelism. If you continue using data parallelism, you have to shrink your batch size so that it fits into single GPU. But on the other hand, in our case, you can use much larger batch sizes and we will still, because we are partitioning the model, the partition will fit into single GPU. So for example, here, transformer model, when you go to 16 GPUs, we can use, 256 as the batch size, as opposed to 1. In one batch size of 1 means that you have to use batch size of 1 so that your model fits into single GPU if you use data parallelism, for example. So basically, PAR-DNN enables working with larger data, pushing larger batch sizes, using the certain number of GPUs, let's say 16 GPUs, etc. The other result that I'm going to show, these are the models, they fit into single GPU, but barely fit into single GPU. Word and character, and this is wide residual network, ResNet, transformer, and this is a video prediction model. So these numbers are GPUs, and in the parentheses, you see the batch sizes. This is what I was trying to say. For example, in the orange, you see a very good scaling, and then in the blue. But for example, with the transformer, we have, the best performance is achieved when you use 8 GPUs. 16 GPU doesn't provide any further improvement because you are limited with the graph, the degree of parallelism in the graph, basically. And same here, 8 GPU is better than 16 GPU. You see a slight improvement in the video prediction. But again, this is not the drawback of our algorithm, but it's the nature of the graphs, that it just doesn't have enough parallelism to exploit 16 GPUs. Okay, so with the larger models, there's no reference point, but because they don't fit into single GPU, they start fitting into 4 GPUs. I can only show the throughputs within PAR-DNN. We have good scaling with large models as well, up to 16 GPUs. So another thing is, we kind of suggest after 16 GPUs, you should, or 8 GPUs, you should switch to data parallelism. So you can have data parallelism within a node, like 4 or 6 GPUs. You will have data model parallelism or PAR-DNN. And then beyond that, across nodes, you will have data parallelism. So you can partition the data between nodes, and within the node, we can do model parallelism. Okay, so we also compared our performance with gradient checkpointing plus data parallelism. As I mentioned, gradient checkpoint is a popular method. The main idea is redundant recompute. So for example, they don't keep all the intermediate data, but instead they recompute in the back propagation. So that saves a lot of memory space. So we have, for most of the time we are better, but there are cases that we are not as good as gradient checkpointing. But there is also one thing, gradient checkpointing has a lot of overhead, and also it doesn't give partitioning or valid solution for large models. When we have a large model, it doesn't produce a valid solution. For example, it fails to fit the model for the percent of the time and runs out of memory. So its solution is actually doesn't obey the memory constraints. But in our case, we don't have that issue. And we also compared with mesh TensorFlow. We are, I would say, on par with mesh TensorFlow. But again, mesh TensorFlow works for transformer models, which is NLP. So it's very specific. Another issue with the mesh TensorFlow is as a user, you need to tell how to partition, so geometry of partitioning. So you have to try different geometries to tune. Here, for example, for 4 GPUs, we tried 2 geometries, and 8 GPUs, we tried 3 different geometries. Again, mesh TensorFlow also, the running time, the overhead is a bit too much to tune these splits, finding the optimal partitioning. So you need to do some tuning. So PAR-DNN, first of all, it automates the partitioning process. There is no need for the programmer to be involved. And also in terms of overhead, we are much better, which I will show in the next slide. So in terms of our overheads, in this table, I'm showing the step 1 and step 2 algorithm, the complexities, time complexities. But in practice, for the very large models, our partitioning time takes only 18 seconds to 2 minutes almost. So this is very fast compared to, you know, the training time. In fact, there is a related work from Google, and their partitioning takes 16 hours or so to give a solution. So compared to those approaches, ours is quite fast, and it's negligible, I would say, the overhead it introduces. Okay, this is my last slide. We address the memory constraint deep learning models. Our approach is basically at system level. We don't deal with deep learning layers or operations, etc. So it's very agnostic about that. It's non-intrusive. We don't need to change the model or the source code or the kernels. There are some approaches doing that, but we are not. And our two-step algorithm provides efficiency and low overhead at the same time. And our results, we are either better or provide qualitative advantages, like we provide a valid solution, we have much lower overhead, or we don't require the programmer intervention. And we submitted this paper, it's under review, but you can, if you want to read the paper in more detail and give us feedback, it's available on archive. Thank you very much. That's all from me.
Awesome. Thank you so much, Didem. Appreciate it. All right, let's see if we have a question from the audience.
Should I stop sharing my screen, or I can continue sharing?
Yeah, you can perhaps leave your slides.
Okay, maybe if there is a question related to the slide, I'll go back. But I'll be happy to answer your questions.
Thank you very much, Didem. It has been very interesting. I just have a question for checkpointing. Do you think that your solution may help people to checkpoint their job?
I didn't get the question. You're asking a question about grading checkpointing, but I didn't get the question.
Yes, because some people find it difficult to checkpoint data machine learning workflow. So I was wondering if your solution can show face to allow them to do that.
So we actually, for our results comparisons, we use the open source implementation of gradient checkpointing, but we had to change the data structures, etc. The open source as it is, it didn't work on the models that we had. It didn't provide any solution, actually, it failed. So we actually improve it a little bit so that it gives us a solution. I'm not sure what other people use as gradient checkpointing, but I think we use original papers repository. I think there were some publications after the original paper improving their algorithm. The thing is that either they are not publicly available, or they are very specific to one model. For example, they need to use it as on a transformer model. They just make it work for that transformer model, so it's not generic that we cannot test in all 10 models that we have.
I see.
Yeah, so our approach is generics. The only thing we need from the user, their model is implemented in TensorFlow. That's our requirement. Like, even though algorithm is agnostic about TensorFlow, our scheduler, like the memory constraint part, is really tied to how the TensorFlow uses its memory, because it treats nodes differently. Like, there are 3 types of nodes. One live throughout the execution. One type is very temporary. The other one, until their output is discarded, then they are deallocated. So these different types of treatments of memory allocation on the nodes may not be the same in MXNet or PyTorch, let's say. So we have to, for those frameworks, we need to adapt this step 2 part, which is the memory constraint part. But the first partitioning part is just profiling the data transfer cost and then the compute times. Those profiling information typically is available through their APIs. Yeah.
Thank you very much.
Thank you. Any other questions?
I do have a few questions.
Yes.
The superlinear speedup in your slide 34, I believe. I think I missed the reason why you having superlinear speedup moving from 1 to 2.
In the paper, we try to explain that. I hope I will be explained. Basically, when you increase the batch size, double the batch size, the compute time doesn't double the same rate. Because, for example, in the batch size, you may, you're doing some matrix multiplication, but only in certain parts doubles, but the rest stays the same, or they increase sublinearly in terms of execution time. That's why we see this super linear, but it's not because of our tool provides that super linear. It's because when you increase, like double the batch size, the execution time shouldn't double, basically. That's why.
Is it related to the number of perhaps iteration? You converging faster because you?
No. It's not because the number of iterations.
Okay.
It's basically not every part of the model is affected about the same rate. That's the main reason. Okay.
Sounds good.
Yeah. I can also point after my email. I will send you the paragraph that we use in I think that explains better. My student will explain better, but in short, basically, not every operations increase at the same rate. That's the main reason we see.
I see. I have another question. SimGrid, are you familiar a bit with SimGrid? You know, this is the tool for many people.
Yes.
Because you had the portion where you know, the partitioning portion, where you try to estimate the memory footprint and doing this before the actual run. I guess from, collected profile data or, I mean, do you see, I mean, how would you distinguish? I mean, I think the step 1 from perhaps what SimGrid offers, or do you see maybe different,
I know so SimGrid, to me, it's it still needs to take an algorithm and kind of simulate its scheduling. So it will still need the order of execution or the partitions from you, isn't it? Maybe I'm wrong, but that's my perception about SimGrid.
Yeah, I mean, SimGrid.
So you will just give the task graph with costs, and then it will.
Right. That's right.
It will partition, or it will it.
So it does not do the partitioning or load balancing. It does not, but it will tell you, the memory footprint, for instance, or
but what we need is what TensorFlow's decision about scheduling. So remember my slide about 2 different schedules?
Yeah.
We are not deciding the schedule. We are not deciding the order of execution. TensorFlow decides. So with the emulation, we are trying to mimic what TensorFlow decides to do. It's it has an algorithm of scheduling. So we are just executing that algorithm to decide, like to see the order. We are not deciding the order of execution.
Very good. Great.
That's offloaded to the TensorFlow scheduler. I think people try to improve the TensorFlow scheduler, but it's not our goal here. Our goal is to map the nodes to the devices, and then we give this to the TensorFlow scheduler, and then it will decide the order of execution.
I see. Very good.
Yeah. Okay. Well, thank you very much for joining.
Thanks, Didem, for joining us on a Sunday. I think it's a off day.
Yeah, I send my kid to park so that he doesn't interrupt me, so I'll go and play with him now.
Thanks for your time, and we're glad to having you with us. And well, I mean, without, I guess, no more question on our side, I'd like to thank again you. And I guess, I don't know when we be able to go on conferences or travel, maybe not anytime soon.
Well, I'm pregnant. Hopefully, I have a baby in 2 months. So,
Congratulations. Okay.
I don't plan to travel till June, anyways. Until maybe after June, maybe. Great. I don't know. But you're very welcome to visit me in Istanbul.
Sure. Sounds good. Great. Thank you so much, Didem. And we'll see you soon, hopefully. Take care. Thanks for your time. Appreciate it.
Take care. Bye-bye. Thank you. Bye-bye.